No matter how miraculous we think life is, even a religious believer who lives in modern times cannot deny that life itself operates within the basic framework of physics. In other words, physics is a more fundamental science than biology. But life? Well, life seems completely different from familiar things like the sun, black holes, or nebulae. So, in the eyes of a theoretical physicist, what is the essence of life? Today, I want to talk with you about some ideas from a book literally titled, What is Life? This classic popular science work on biology was written by Erwin Schrödinger. Most people know Schrödinger for his contributions to quantum mechanics. For example, the famous thought experiment, Schrödinger's cat. These days, Schrödinger's cat has practically become synonymous with quantum mechanics. What you may not know is that Schrödinger also made a very important contribution in the field of biology. In addition to being a renowned quantum physicist, he was one of the founding figures of what today is a cutting-edge field, molecular biology. His reflections on biology are largely concentrated in this thin little book. In What is Life? Schrödinger focused on the central question of life's nature by exploring three key issues. The first question: what does life use to reproduce and inherit its characteristics? It was Schrödinger who predicted that life passes hereditary information to the next generation through genes, and that genes are essentially a kind of aperiodic crystal. What an aperiodic crystal is will be explained in a moment. The second question: what allows life to continuously evolve? Schrödinger believed it is precisely well-timed quantum jumps that lead to gene mutations, which in turn make evolution possible. These quantum jumps serve as a bridge between quantum mechanics and life science. The third question: what does life rely on to maintain its operations? Schrödinger proposed that life feeds on negative entropy. That is, it survives by continually absorbing order from its environment to sustain itself. Next, let's delve into these three questions in detail. Reproduction and heredity are the foundation of life's continuity. If we want to understand the essence of life, this topic is unavoidable. So let's begin with the first question. What does life use to reproduce and pass on its traits? Schrödinger believed that the substance life uses for heredity, in other words, genes, must be a kind of aperiodic crystal. But why would he say that? Why does a gene have to be a crystal, and why specifically aperiodic? To answer this, we have to start by looking at the size of living things. Life forms on Earth come in an astonishing variety of sizes. On the large end, you have whales and elephants, and on the small end, you have single-celled organisms. Their volumes differ enormously. Yet all these life forms have one thing in common. They're made up of cells, and even the tiniest single-celled organism contains billions of atoms. In terms of atoms, actually all living things are extremely, extremely large. If we really press the question, why does life need to be so big? Why couldn't something made of just 20 or 50 atoms also be alive? The answer is simple. With so few atoms, it would be impossible to form a stable living structure. At this point, we have to dig down to physical laws. For life processes to occur, they must obey certain physical and chemical laws. That way, all the reactions inside a cell won't devolve into a completely chaotic mess. However, and this might be counterintuitive, the vast majority of so-called classical physical laws are actually statistical in nature. These laws don't really apply to individual atoms or very small numbers of atoms. You see, in the microscopic world, every atom is constantly undergoing random thermal motion. The higher the temperature, the faster this random motion. And by random, we mean truly random in the literal sense. In short, an atom's motion doesn't follow any fixed pattern or rule. Physics cannot determine or predict the exact state of motion that a particular atom will have at some specific future moment. It's only when the number of atoms becomes very large that the overall system's behavior becomes more predictable, and only then do the laws of physics start to explain the collective behavior of those atoms. For example, Imagine a sealed container filled uniformly with a cloud of fog, which is really made up of countless tiny water droplets. If you observe this fog, you'll find that, just as we'd expect, it's influenced by gravity, and as a whole, it slowly settles downward. But if you zoom in with a microscope and watch a single microscopic water droplet, you'll discover that the usual physical law seems to break down for it. That tiny droplet doesn't drift straight down smoothly like the fog cloud as a whole. Instead, it falls along a wildly irregular path, sometimes veering left, sometimes right, even sometimes hopping up a bit. Overall, it wiggles downward like a little snake, and we have absolutely no way to predict that snake-like trajectory in advance. Why does this happen? It's because these droplets are so small that individual atoms or molecules in the air are constantly colliding with them and knocking them about, changing their motion. Only when there are enough of these droplets, or enough atoms in an object, do all those random jostling motions tend to average out. At the scale of the entire fog cloud, the random kicks largely cancel each other, and so the fog as a whole follows the smooth behavior that physics predicts. So, for a living organism to exist, it must be large enough that physical laws can reliably escort its most basic life processes. In other words, a living thing has to be sufficiently big for the laws of physics to safeguard its fundamental activities. How big is big enough? Schrödinger didn't give a precise number for that. However, he did propose a guideline called the ρ(n) rule, the square root of n rule, to gauge how accurate the laws of physics will be for a system of a given size. For example, suppose you have 100 molecules. The square root of 100 is 10. That implies roughly 10 out of those 100 molecules might behave in ways that deviate from the normal physical law. In other words, about a 10% error. If you have 1 million molecules, the square root is 1, 0. In that case, about 1 molecules might misbehave, which out of a million is only 0.1%. Clearly, the more particles you have, the smaller the relative effect of those erratic stragglers, and the more precisely the system's behavior conforms to physical law. Only when the precision gets high enough can life emerge. Here's a mind-bending thought. On the scale at which we humans observe the world, almost everything seems very orderly and predictable. But in the eyes of a bacterium, perhaps the world's very nature includes a bit of uncertainty. A bacterium might experience a slightly fuzzy, unpredictable world, a perspective of reality that living beings at our larger scale can never directly perceive. Now, this brings us to a new problem. Scientists, by observing the size of structures like chromosomes inside cells, deduced that genes themselves must be extremely small, perhaps on the order of only 1,000 atoms, if not fewer. With so few atoms, by rights, a gene should be subject to violent, random thermal agitation and be highly unstable. Yet, in reality, living organisms, humans included, can maintain genetic stability over very long periods. Humans today aren't significantly different from humans 1,000 years ago, genetically speaking. So how does a gene that small resolve this contradiction, remaining stable despite the expected instability? Traditional physics had no answer for this, but quantum mechanics, whose domain is precisely the microscopic world of atoms, offered a clue. As a master of quantum theory, Schrödinger made a bold prediction. The atoms in a gene are held together by a special kind of force described in quantum mechanics, something called the Heitler-London force. Through chemical bonds governed by this force, the atoms in the gene form an extremely orderly crystal structure. In such an orderly structure, the atoms are no longer so easily disturbed by random thermal jiggling, which allows the gene's internal structure to remain intact for a very long time. The Heitler-London quantum mechanism essentially glues the atoms tightly together into a stable configuration. By stable, we mean that it would take a lot of energy to break this configuration apart. And such a large jolt of energy is exceedingly unlikely to appear at random inside an organism, though not entirely impossible, just very improbable. Now, hearing this, Does it remind you of anything? That's right, it makes one think of the random gene mutations that can lead to cancer. Our bodies do experience spontaneous gene mutations, but the probability is low under normal conditions. However, when a living organism is exposed to high-energy radiation, the chance of gene mutation shoots up. This is what we commonly refer to when we say radiation causes cancer. Fundamentally, high-energy radiation is carcinogenic because it delivers a huge amount of energy that can break those strong Hitler-London bonds holding a gene's atoms together. All right, moving on. Stability alone isn't enough for a substance to serve as life's hereditary material. To be the carrier of genetic information, genes also need to store an enormous amount of information, something ordinary crystals cannot do. Schrödinger argued that genes are not ordinary crystals at all, but rather a special kind of non-periodic crystal. What is a crystal in this context? A crystal is a solid formed by a large number of atoms, ions, or molecules arranged in an orderly pattern according to certain rules. Schrödinger divided crystals into two categories. One category is periodic crystals, meaning their internal structure repeats over and over in a regular periodic pattern. For example, common table salt, a sodium chloride crystal, and ice are in this category. Inside such crystals, the atoms or molecules are arranged in a fixed pattern that just repeats itself periodically. That repeating pattern is very monotonous, so there isn't much complexity in it. It really can't store much information. The other category is aperiodic crystals, non-periodic crystals. As the name implies, the internal structure of these crystals is not periodic. The arrangement of the building blocks keeps changing instead of repeating in a uniform pattern. This sequence, in which the units are arranged, can be thought of like a long code. And just like a code, it is capable of storing a huge amount of information. Knowing that life's hereditary material is stable is only half the story. The evolution of life has two sides. On one side, there is stability. Because of the stability of that aperiodic crystal structure, life can ensure that its genetic information is passed down through many generations with minimal changes. On the other side, there is variation. Variation in the form of mutations is extremely important, because it is mutation that makes evolution possible. Mutations allowed life on Earth to develop from the very earliest single-celled organisms into the millions of species we see today. In short, genes need to be highly stable, and at the same time, mutations in those genes are indispensable. This is because the natural environment is always slowly changing. For life to survive, it must continuously adapt to its environment by adjusting its traits. And those adjustments ultimately come from genetic mutations. Mutation is the prerequisite for life to keep adapting and evolving. Now, when we say life needs mutations, we don't mean that organisms actively choose to mutate. Rather, any life form that lacked genetic variability simply wouldn't continue to exist. Conversely, though, the rate of mutation can't be too high either. It has to remain a rare occurrence to keep up with the slowly changing environment on Earth. Mutations can be beneficial or harmful. Some mutations might help an organism better adapt to its environment, but many more could disrupt or damage traits that have already been finely tuned for survival. After all, mutations are random. No one is controlling whether a particular mutation will be good or bad. If mutations happen too frequently, the harmful ones would far outnumber the beneficial ones. That wouldn't aid a species in adapting. In fact, it would likely stall a species' evolution or even lead to its extinction. So maintaining a balance between stability and mutation is extremely important. How then do genes find this balance between being stable and being able to mutate? Schrödinger had a profound insight here. Quantum mechanics can provide the perfect explanation. Gene mutations, he suggested, are actually caused by quantum jumps occurring within gene molecules. We know from quantum physics that when a microscopic particle transitions from one energy state to another, it undergoes a quantum jump. Atoms and molecules each have certain allowed energy levels, and generally the lower the energy of a molecular configuration, the more stable that molecule is. Genes are no exception. A stable gene molecule has a relatively low energy state and can persist in that state for a very long time. It's only when the gene molecule absorbs a specific amount of energy from outside that it makes a quantum jump to a different energy state. The result of that quantum jump is that the arrangement of atoms inside the gene changes. In other words, a mutation occurs. This part is a bit tricky to grasp, but it's very important. If you didn't quite catch that, feel free to rewind a few seconds and listen again. Now, an important question arises. If a gene does mutate, then on the microscopic level, that quantum jump has given the gene molecule a higher energy than it had before. In that higher energy form, the gene should be less stable. Wouldn't it eventually just jump back to its original state? If a mutated gene could easily revert on its own, then that mutation wouldn't have much lasting meaning at all. And that brings us to another key characteristic of gene molecules, something called isomerism. For organic molecules, isomers are actually a pretty common thing. Isomerism means that you can have two molecules made of exactly the same atoms, the same kinds and numbers of each atom, but those atoms are connected in a different order, leading to completely different structures and properties for the two molecules. For example, propanol and isopropanol are a simple pair of isomers. Both molecules consist of 3 carbon atoms, 1 oxygen atom, and 8 hydrogen atoms. The 3 carbons are linked in a short chain. The difference is that in a molecule of propanol, the oxygen atom is attached to one end of the carbon chain, whereas in isopropanol, the oxygen atom is attached to the middle of the carbon chain. This difference in how the atoms are arranged gives the two molecules entirely different physical and chemical characteristics. Schrödinger predicted that gene molecules are a kind of aperiodic crystal composed of isomeric units. This kind of structure can use as little material as possible to store as much information as possible. And a gene mutation is essentially the process of the gene molecule absorbing energy and undergoing a quantum jump, changing from one isomeric form into another isomeric form. Both isomeric forms of a molecule can be quite stable. Each one has a low overall energy, and they don't have any inherent tendency to turn into each other. That's because transforming from one configuration into the other requires going through an intermediate configuration that has a higher energy than either of the stable states. It's as if each isomeric form sits at the bottom of its own valley, energy-wise. To get from one valley to the other, the molecule would have to gain enough energy to climb up over the mountain peak between them and then descend into the neighboring valley. The energy needed to climb that mountain is very high, so under normal circumstances, the molecule will not spontaneously convert from one isomer to the other. In practical terms, this means that once a gene has mutated, switching to a different isomeric configuration, it won't easily change back again on its own. In order for a mutation to occur in the first place, the gene molecule must acquire energy beyond a certain critical threshold from the outside. And it so happens that the amount of energy required to make a gene molecule undergo one of these quantum jumps is quite high. This is why mutations naturally occur at such a low rate. As we mentioned earlier, scientists have found that if you shine X-rays on a cell's genes, the mutation rate will skyrocket. That's because X-rays carry a lot of energy, and when they hit the genes, they can dramatically increase the energy of those gene molecules, triggering quantum jumps. Under normal natural conditions, by contrast, the primary source of energy that can induce these gene transitions is the random fluctuations of thermal motion. The probability of those fluctuations delivering just the right amount of energy is much lower. Only in extremely rare cases will a molecule happen to pick up more than the critical amount of energy it needs to jump to a new state. And here's the most amazing part. Nature, in choosing DNA molecules as the genetic material for life, essentially fine-tuned the energy required for these quantum jumps so that mutations occur at just the right rate. Mutations are rare enough that they don't happen too often, but not so rare that they never happen at all. In other words, nature found a perfect balance, ensuring high stability of the gene while still allowing occasional mutations for evolution. Schrödinger didn't stop at reproduction and evolution. Going beyond those, he stepped back to look at life from a broader, more macroscopic perspective to investigate the fundamental mechanism by which life sustains itself. We can pose the question like this: under what conditions would we say that a lump of matter is alive? Everyone might have their own answer to that. Schrödinger's answer was that being alive means that an object will actively and continuously carry out some activities. For example, it will keep moving, keep exchanging matter with its environment, and so on, and it will sustain those activities for far longer than an inanimate object would under similar circumstances. For instance, a rock can move too. It might roll down a hill, but it won't be long before it comes to a stop. A person, on the other hand, can keep moving in one way or another throughout their entire life. So why is it that non-living objects can't continue doing something indefinitely? Because if a system has no life in it, when you place it in an isolated, closed environment, all of its motions will obey the simplest physical principles and, due to various forms of friction or resistance, they will quickly come to a standstill. The charge in a battery will gradually be used up. The fire in a brazier will gradually burn out. After that, these non-living objects will just turn into a collection of inert matter, settling into a static, unchanging state where nothing else happens. Physicists call this kind of unchanging, inert state maximum entropy. For a non-living object, that dead, motionless state basically means that the level of disorder in the system has reached its highest possible value. In this state, because of heat exchange, the temperature within the system becomes completely uniform, which is why it's also referred to as thermal equilibrium. In fact, everything that happens in nature is accompanied by an increase in entropy in the part of the world where it's happening. All things obey this principle, and life is no exception. Whether we are walking, breathing, or our hearts are beating, at every moment all living creatures are increasing their internal entropy. And when does that entropy buildup finally end for an organism? Of course, it's when the organism's entropy has increased to the maximum and can go no higher. At that point, all the atoms that make up the organism will have returned to the cosmos in a state of complete disorder, essentially getting reshuffled into the universe's particle pool, dust to dust, ashes to ashes. Naturally, the endpoint of this rise in entropy is death. At the microscopic level, that means the death of an individual. At the macroscopic level, it can mean the extinction of an entire species. So, to prolong life, how do living things respond to this relentless march toward entropy? Schrödinger's insight was that life survives by feeding on negative entropy. Now, what is negative entropy? It's actually not hard to understand. Since entropy is a measure of disorder in a system, negative entropy is just the opposite. It's a measure of order in a system. In other words, through metabolism, a living organism brings into itself a constant stream of negative entropy. In plain terms, a constant stream of orderliness to compensate for the positive entropy disorder that its life activities are producing. Building on this analysis, Schrödinger put forward his famous idea that life feeds on negative entropy. He said that an organism has an amazing ability to concentrate the order that exists freely in nature and incorporate it into itself. In other words, a living thing can extract orderliness from its surrounding environment so as to prevent its own atoms from sliding towards chaos. From this point of view, the reason life is so remarkable is that it can continuously acquire negative entropy in a world where entropy is always increasing. Schrödinger's exposition here hits upon the most fundamental principle behind life's activities. He was using the perspective of physics to explain the basic problem of biology. And truly, great ideas are not confined by the boundaries of any one field. They can transcend time and space, exerting a profound influence on the world and giving future generations much to reflect on. But now we must add an important caveat. Seeing Schrödinger's ideas from today's standpoint, we have to maintain a rational skepticism as well. After all, Schrödinger published this book in 1944. In the decades since then, many scientists standing on Schrödinger's shoulders have propelled the life sciences far forward. When they look back at what is life, quite a few scholars have criticized the notion of negative entropy for creating a fair bit of confusion in understanding life. The most straightforward issue is that many ordinary readers find it hard to distinguish negative entropy from energy. Schrödinger's proposal didn't describe any concrete mechanistic process. It only described an end result, namely, that an organism relies on negative entropy to maintain the orderly organization of its structure and the functions of its cells, while dumping the generated heat into the environment. Schrödinger himself didn't know, and thus didn't explain, how an organism actually obtains this negative entropy. The phrase "feeds on negative entropy" was meant as a metaphorical description. Schrödinger even suggested that in order to rigorously explain life in terms of negative entropy, scientists might have to discover a new law of physics. Furthermore, if we loosely define life simply as feeding on negative entropy, the definition itself runs into problems. Non-living things can also utilize low-entropy energy. A gasoline engine, for example, is a case in point. It takes in fuel, which is a low-entropy source of energy, and produces motion and waste heat. However, one can counter this counterexample by pointing out that an engine only manages to utilize negative entropy because it was designed and built by humans, and those humans had to consume an even larger amount of negative entropy in the stale process of designing and building the engine. The biggest problem with the negative entropy concept, though, isn't any single counterexample. The real issue is that the idea is almost too easy to understand, and combined with being somewhat imprecise, it became too popular for its own good. It spread far and wide, leading to a lot of misinterpretation and overinterpretation in fields far removed from physics or biology. For instance, nowadays you'll hear many business executives say, "Life feeds on negative entropy. Entropy represents chaos." So a company must be well ordered and have strict hierarchy in order to thrive like a living organism. Whether that management philosophy is right or wrong isn't our concern here. But it's clearly an appropriation of scientific jargon, grabbing a term from physics that's easy to grasp, but not using it in a scientifically accurate way. By the time concepts like these get transplanted into the business world, they've lost any real connection to their original meaning in physics or biology. Today, we've discussed both the strengths and the shortcomings of Schrödinger's ideas. In future episodes, we'll talk about a lot of other frontier research in the science of life. But no matter what, we should never let the historical limitations of Schrödinger's perspective make us undervalue his contributions. It was precisely Schrödinger's deep insight into life's underlying logic that profoundly influenced the researchers who followed him, leading them in directions that produced the great scientific breakthroughs we enjoy today. All right, we'll wrap up our discussion of this book here. What is Life is still available to buy, and it's quite a thin volume. My explanation here has been purely from a popular science point of view. I've been speaking in plain language. If you'd like to experience the writing of a physicist, a style that's a bit old-fashioned and serious, yet full of wisdom, you might want to pick up the original book and give it a read. Okay, that's all for now. Let's talk more next time.